Hello everyone. In this current video tutorial, we are going to discuss something regarding modified Goodman diagram for torsional shear stress. Up to, today's discussion also belongs to course outcome 3, CO3, wherein to investigate and determine fluctuating stress with respect to finite and infinite life of component under simple and combined loading conditions like transmission shafts using modified Goodman criteria. Now, up till now, we have already discussed predominantly two type of fluctuating stresses are present in a machine part subjected to fluctuating load. Fluctuating load causes fluctuating stresses, and fluctuating stresses are predominantly divided into two categories: completely reverse stress, wherein sigma m, that is mean stress or average stress, is equal to 0. Its nature will be plus minus sigma. Sigma max will be equal to sigma minus sigma mean. In this category, two type of numericals can be asked in your examination. One is for infinite life of the machine part, and another is finite life of the machine part, wherein they may ask you to find out the dimensions of a machine part subjected to completely reverse stress and having expected life of finite. That means finite life is signified by a life less than 10 raised to 6 stress cycles. They may ask you to design the machine part, means to find out the dimension. They may ask you to find out the expected life of the machine part, or the numerical may be based on cumulative fatigue, which will be solved using Minor's equation. The second predominant type of the fluctuating stress is fluctuating stress itself, and there are two different type of numericals they may ask you as regards to fluctuating stress. The numericals based on Soderberg, Goodman or Gerber line, and another type is the numericals based on modified Goodman diagram. Up till now we have already discussed how to solve the numericals based on modified Goodman diagram, but those were wherein the fluctuating stress was of direct stress, nature of direct stress. And now in this today's discussion, we are going to discuss the design of machine parts subjected to fluctuating stress, which is of torsional shear nature. Up till now, we have considered the modified Goodman diagram for designing the machine parts subjected to fluctuating stress, wherein the nature of the fluctuating stress is direct one. That means sigma m was not equal to 0. For such cases, we have used modified Goodman diagram. But in today's discussion, the fluctuating stress will be of tau max to tau min, will be varying from tau max to tau min, means it will be of torsional shear nature. It will be varying from tau max to tau min, and in such case, how to use modified Goodman diagram as applicable for torsional shear, that we are going to discuss today. Now, whenever a machine part is subjected to fluctuating torsional shear stress, which varies from tau max to tau min, following the usual procedure, mean torsional shear stress, mean or average torsional shear stress, tau m will be calculated as tau max plus tau min divided by 2. And amplitude of torsional shear stress, tau a, will be calculated as tau max minus tau min divided by 2. This is same as in case of fluctuating stress, wherein the nature of the stress is direct stress one. Here another difference besides torsional shear is getting induced inside the machine part, which will be of fluctuating nature. In such cases, here we have to take into account the endurance shear strength of the material, endurance shear strength of the machine part, and instead of yield point tensile strength, we have to take into account shear strength SSY of the machine part. Now, how to calculate endurance shear strength and shear strength of the machine part or material of the machine part, that we are going to discuss now. Now there are two different theories based upon which value of endurance shear strength and shear strength of the material is calculated. Based on the distortion energy theory, the endurance shear strength SE is calculated as 0.577 times SE, where SE is the endurance strength of the machine part, and SSY, the shear strength, is calculated as 0.577 SYT, where SYT is yield point tensile strength. If you want to apply shear stress theory, then in such case, the endurance shear strength SSE is given as half of the SE, where SE is the endurance strength of machine part, and SSY, the shear strength, is given as half of the SYT, where SYT is the yield point tensile strength. So in the problem statement, they will provide the information regarding which theory is to be implemented. If not specified, you can employ shear stress theory, and based upon which you can calculate SSE as 0.5 times SE and SSY as 0.5 times SYT. Now the modified Goodman diagram for torsional shear will look as specified here. It will have predominantly two lines. One line joining the SSY on y-axis to SSY on x-axis. Now you can see here on x-axis mean torsional shear stress is considered. On y-axis amplitude of torsional shear stress is considered. A line joining SSY to SSY, SSY on y-axis to SSY on x-axis is the shear line. Here SSY is shear strength. Another line is a line parallel to x-axis, and it is having y coordinate as SSE. Another line, line AB, is parallel to x-axis, and its equation is equal to y coordinate is equal to SSE. Here, instead of x and y, we have to refer SSM and SSA. Therefore, equation of line AB will be SSA y coordinate SSA is equal to SE. Equation of line AB will be SSA, the y coordinate is equal to SSE. It is the line parallel to the x-axis. SSA is equal to SSE is the equation of line AB. Now SSA is equal to what? Tau A multiplied by factor of safety, where tau A is the amplitude of torsional shear stress. So using tau A multiplied by factor of safety in place of SSA, we can write tau A multiplied by factor of safety is equal to SSE. Now adjusting the term, we can write equation of line AB as tau A is equal to SSE upon factor of safety. Equation of line AB will be equal to tau A is equal to SSE upon factor of safety. Now, as far as line joining SSY on y-axis to SSY on x-axis, that is line BC, is considered. Here, x coordinate divided by x intercept plus y coordinate divided by y intercept is equal to 1. Equation of any line can be expressed in this form. Now here x coordinate is SSM, x coordinate, x intercept is SSY, plus y coordinate is SSA, y coordinate is SSA, y intercept is SSY, y intercept is SSY is equal to 1. Now this SSY in the denominator is common, that can be considered as a numerator on the right hand side. So this equation can be simplified as SSM plus SSA is equal to SSY. Now SSM is given by tau m factor of safety, SSA is given by tau a multiplied by factor of safety. So replacing SSM and SSA by tau m factor of safety and tau a factor of safety respectively, one can write summation of these two is equal to SSY. But here factor of safety is common, and this common factor of safety can be considered on right hand side in the denominator. So therefore equation of line BC becomes tau m plus tau A is equal to SSY upon factor of safety. Equation of line BC will be tau m plus tau A is equal to SSY upon factor of safety. Now we have found out equations for both the dominating lines, line AB and line BC. Now intersection of line AB and line BC, that is point B, point of intersection of these two dominating lines is considered as critical point. Critical point will subtend angle theta critical with x-axis. This critical point, point B, will subtend angle theta critical with x-axis. Now, if the angle of a design point is greater than theta critical, then line AB is the dominating line. Line AB governs the design. We have already discussed this while considering modified Goodman diagram for direct stresses. If theta is greater than theta critical, theta for the design point is greater than theta critical, then that will lie in this region wherein the governing line will be line AB. If theta is greater than theta critical, AB will be the governing line. As against, if theta of the design point is smaller than theta critical, then line BC will be governing line. Line BC will be governing line. So, based on the value of theta and theta critical, one can decide which one is the governing line. If theta is greater than theta critical, then the design point will lie in this triangular portion ABO and line AB will be governing line. If theta is smaller than theta critical, then the design point will lie in this triangular portion BOC and line BC will be governing line. The equations of both the line AB and line BC are known to us, and accordingly, based on the value of theta and theta critical, we have to decide which line governs the design and which equation is required to be taken into account for further design of the machine part. Now here one point to be noted, the theta, that is angle subtended by design point with x-axis, is given by theta is equal to tan inverse of tau A upon tau m. Tau A is the amplitude of torsional shear stress, tau m is the mean torsional shear stress. And theta critical is given by tan inverse of SSA, the y coordinate of point B, and divided by SSM, the x coordinate of point B. X coordinate of point B is SSM, y coordinate of point B is SSE. So SSE represents opposite side and x coordinate SSM represents adjacent side. Opposite side upon adjacent side, that represents tan of angle. So tan of theta critical will be SSA upon SSM, and theta critical will be tan inverse of SSA upon SSM. Now from the line AB is equal to SSA is equal to SSE. From the equation of line AB, SSA is equal to SSE. So here in this case, while calculating theta critical, tan inverse of SSA upon SSM. So from line AB, we can note SSA is equal to SSE. SSA is equal to SSE. Whereas from equation of line BC, we can note that SSM plus SSA is equal to SSY. So SSM plus SSA is equal to SSY. The same thing I have just repeated over here. Now, in this case, we are aware that at point B, SSA is equal to SSE. SSA is equal to SSE. So, using that here, we can write SSM is equal to SSY minus SSA, but SSA is equal to SSE. Therefore, SSM is equal to SSY minus SSE. So the quantities SSA and SSM as required while calculating theta critical can be calculated using these relations. SSA will be directly calculated or assumed as SSE, whereas SSM is equal to subtraction of the SSE from the SYT. That represents SSM. So knowing the values of SSA and SSM, one can calculate theta critical, and having tan inverse of tau A upon tau M, one can calculate theta. Based on the value of theta and theta critical, we have to take into account, we have to decide which line governs the design, and accordingly its governing equation is required to be taken into account while calculating the dimensions of the machine part or while designing the machine part. So here in this particular video tutorial, we have again gone through what is fluctuating load, how to calculate mean and amplitude of stress for fluctuating load. If the load is torsional shear 1, torsional load which will be inducing torsional shear stress inside the machine part. What are the equations of Soderberg and Goodman lines, and what is the modified Goodman diagram for torsional shear and how to use it, that we have seen in this video tutorial. So that's all in this today's discussion. Thank you.